Okay, hello everyone. It's my pleasure now to introduce Professor Nimal Viswanathan from University of Hyderabad. I'll just speak a few words about him. Professor Nimal Viswanathan received his PhD from the University of Hyderabad in 1997. He then joined as a reader in the same institute in 2006. Currently, he is a professor in the School of Physics, University of Hyderabad. He has over 150 publications in reputed journals and hold an expertise in the fields of singular optics, angular momenta beams, and topological optics. Today he will speak to us on the spin-orbit interaction of light, and he'll share his thoughts about it and on the general growth of the field. Thank you, Professor Viswanathan.
Thanks for the introduction, and thanks Nityanandan for persisting that I should visit Hyderabad IIT and give a talk. I was supposed to be here for the previous occasion when he organized a conference in honor of Professor Porcerian, who was his guide and my friend, but I was not around at that time, so I couldn't attend. Anyway, I should thank Professor Omatsu for share the screen. It is done, right? It is shared. It's coming. Yeah. So, for introducing this general field of structured light, by the way, so feel free to stop me at any point. This is more or less an informal session, so even if it goes a little bit away from the scheduled time, it should not be a problem. So this comes under a general field of structured light, and different people interpret this area of research in different ways, and I want to present it as though this structured light field is part of spin-orbit interaction of light. And contrary to what Professor Omatsu did, my light that I'm going to talk about will not touch the material till the last part of the talk, which is the last 1/3 of the talk. So till that time, I will simply talk about the fascinating things just about light, nothing else. So that essentially means that there is a lot more things that we need to understand just about light before even it starts interacting with any material, right? So that is essentially the main idea behind this one. So you have seen similar such thing in Professor Omatsu's thing. Light can spin, twist, dance, all kinds of things it can do. So some part of the talk will include that. One thing that Professor Omatsu did not touch upon, towards the end he mentioned, but that will be the part of my talk, is that he talked about orbital angular momentum of the light beams. So, but I am going to introduce one more degree of freedom into that, which is the spin part of it. That means that the light has both polarization and the modal part of it. So then we will talk about how they interact. Okay. So before we get any further, let us even understand our misunderstandings. There are a lot of things that we have been taught. I was also a student once upon a time. Many things we have been told which are actually not correct, and because the teachings that has been done about light was so limiting that when new things started emerging, it became difficult for us to kind of understand, and it took some time to catch up. So we all were taught that light is monochromatic, but actually it is not correct. It is actually quasi-monochromatic. Because all these things you will realize that they are going to play a very, very important role as we move forward on how the new areas are emerging. And we were also taught that laser light is a plane wave. It is not. It is a paraxial wave. That means that the beam, if you look at it, that is what I have given a schematic here. If you say that this is the source, the laser box is ending here. After that, when it comes out, the beam is diverging. That means that if I shine the laser till the end of the room, you see that the spot here and the spot at the end of the room are big at the end of the room. That means that it is diverging. So it cannot be a plane wave because plane waves do not diverge. If you look at from the Maxwell's equations point of view, divergence of E equal to 0 in vacuum. But for a laser beam, divergence of E is not 0. That is why it diverges. So you have to kind of keep that in mind. So it is not a plane wave, but it is a paraxial wave. And I am adding two more terms to that. It is not a wave, but it is a beam. Because it is a beam, it expands. Because later on you will see that it is an electromagnetic beam, and it has a field nature. That means E and B are there, electric field is there. And so these are the new terminology, is that it is a beam field or a wave beam field. It has a combination of all these properties that one has to kind of keep in mind. And we were also taught that it propagates in a rectilinear fashion, which is not correct. It travels in a curved path. That is why it diverges from here to there. If you track it, you will see that it is going in a curved trajectory. Later on, you will see that it can travel in a helical trajectory also. It can travel in whichever trajectory that it chooses. Let us not restrict it and say that it is only a rectilinear propagation, which makes it that it travels in straight line. It is actually not correct. And we were also taught that laser light, or a light in general, is uniformly polarized. That means that if you take a beam and then you polarize it or send it through a polarizer, it is a plane polarized light. It is not correct. Even if I polarize a beam of light along the x-axis, because of the fact that the beam is diverging and the wavefront of this beam has curvature associated with that one, automatically the EY component will come, which is orthogonal to that. And because of the curvature, there is also a Z component that comes in. So actually an electromagnetic beam field has all the three components, not just the EX component. It has the orthogonal and the longitudinal component. These two together are the transverse, and this is the longitudinal component. And we were told that light carries a linear momentum. This is what starts from the fact that your comet always has its tail in a direction away from the sunlight, because the light from the sun puts some linear momentum onto the comets and then it pushes it away from that. But subsequently people realized that it also carries a spin angular momentum. That means that the photons or the electromagnetic wave can spin around itself, or we'll come to it in a bit. And then it can also carry orbital angular momentum. That means that it can precess around a trajectory. That is what Professor Omatsu's talk emphasized on. Now, the general thought process is that, but these additional things that I am talking about are very, very small. We will just neglect it, kind of a thing. But that was the bad thing that people did long back. Because of that, the complete understanding of light and these fundamental characteristics right from the Maxwell's equations, most of it were missed because we were saying that it is too small and it can be ignored, and we simply removed all these other two components, and then we said that it is only the EX component that is predominant in this one. But if you don't ignore, then a lot of interesting things happen. So my point of view is that no, you cannot ignore that. You have to necessarily take this as a three-dimensional field, and then let us see what are the new things that it is going to offer us. So that is basically clearing up all the incorrect things that we have been taught. Right? Once you remove those things, a lot of interesting things will come. And my talk is going to be addressing some aspects of it. So I will provide an overview of my talk and a little bit of background. And then we will jump into the spin and the orbital angular momentum aspects of light. And then because of that, there is a new idea of geometric phase, or some people even call it in a very limited fashion as a Berry's phase, comes into picture. That is necessary for us to understand where the spin orbit interaction of the light is coming from. And then I have divided the remaining part of the talk into two aspects. One is Because of this spin-orbit interaction, what are the manifestations of that? Three things I will talk about essentially. One is the spin-orbit coupling, conversion. That means that you can convert spin angular momentum to orbital angular momentum. And there is a spin Hall effect, like similar to the Hall effect that one studies in condensed matter physics. There is a Hall effect that comes in light also. And then there is an equivalent one as far as the orbital angular momentum is concerned, which is the orbital Hall effect of light. So this forms one subset of one class of some effects that are essentially a subset of this spin-orbit interaction of light. All these things happen because the polarization of light is no longer uniform. It is not homogeneously polarized. It is inhomogeneously polarized beams that you have. And I will give some examples of what happens to, or where does this inhomogeneity come from by sending the light through an optical fiber or through optical crystals, graded index, or even if you focus it. And the interesting thing is that even the simplest of the optical processes, that if you take a beam of light and reflect it from a glass surface, which is almost the first chapter in any optics book, that you have a lot of interesting things that one has to worry about, right? So that is essentially the last thing, saying that all these other materials and medias are much, much more complicated than the simple dielectric interface, and a lot of interesting physics comes out of that. And towards the end of it, I will just touch upon a couple of applications that we have looked at in this context. Okay, spin-orbit interaction of light. It's just a general overview. Most important thing that you have to keep in mind is that it is a fundamental in origin, and it is very, very generic in the sense that every spinning object, whether it is macroscopic, microscopic, nanoscopic, atomic level, any spinning object intrinsically has a spin-orbit interaction coupled to it, right? So one thing that you can see is that Earth is spinning around its axis, and it is also spinning around the sun's trajectory, that one can look at it in various different ways. So particle spins, and then it also goes around the trajectory. So this part spinning around its axis is the spin angular momentum, that if it goes around a axis, then it is the orbital angular momentum. Photons do that, or electromagnetic waves can do that. So that is what forms a part of this whole thing. This spin-orbit interaction basically plays a very important role in all areas of physics. The most important thing that it started with is the condensed matter physics, and you have read all the Hall effect and things like that. That comes because of the spinning electrons. It played an important role in the high energy physics also. And in this whole thing, optics and photonics is the recent entrance. Recent meaning probably couple of decades back it started. So now we are looking at the spin-orbit interaction in the context of optics and photonics. Important thing is that every optical process that you have studied already has a spin-orbit interaction associated with that one. That means that a propagating beam of light, whether you reflect or refract, diffraction, scattering, focusing, any optical process that you have studied intrinsically has spin-orbit interaction associated with that one. It may be a very small effect, but if you can measure it, you can quantify that aspect, right? So that is essentially the bottom line of this whole thing. And we are looking at very, very inherent property of light, and later on we will look at how that aspect of light interacts with the matter, and what are all the new things that we can learn about it. And as I said, it is in the nano-optics when you interact with metamaterials, photonic crystal, all kinds of things that this kind of light can interact, and new effects come into the picture. And as Omatsu said, that this whole area is known as singular optics, or some people even call it, the modern terminology is the structured light area of research. So the thing that you have to keep in mind is that spin and orbital angular momentum, degrees of freedom, are not independent of each other, but they are coupled. So these are the 2 degrees of freedom, and they are coupled. That essentially means that if an object is spinning, and it will take a trajectory which is different, whether it is spinning clockwise or counterclockwise, it will take a 2 different trajectory, right? You take a ball and then you spin it like this or you spin it like this, it will take two different trajectories. That is your spin-orbit interaction. So the spin basically decides the trajectory, which is the orbit part of it, and the orbit decides the trajectory. So if this is going to take in this direction, it will spin in a particular way. If it takes a direction which is different, it will spin in a different way. Right? All these things are very, very well known to people like Ravichandran and Ashwin. Right? That is something that you should keep in mind. But they will not understand it as a spin-orbit interaction, but it is our job to make sure that the physics part of the spinning photons or spinning electromagnetic waves is understood properly, because it is going to lead to a lot of interesting things. So as I said, light carries both the spin and orbital angular momentum, determined by the polarization, whether it is circularly polarized, and later on you will see that the spatial modal part of it carries the orbital angular momentum part of it. And the separation of these two is an ideal situation, similar to what I said, that if you have a plane wave kind of a thing, but there is no plane wave, it is an ideal situation. In a real wave, you see that the spin and orbital angular momentum degrees of freedom of light are always coupled with each other. This is a generic property. As I said, this is there in all the cases in which you consider a beam of, and when you say that it is a quasi-monochromatic beam. And the coupling is a parameter that you can control. How much of coupling that one can do, it depends on how the light or the degrees of freedom of light are made to couple with each other. We have some control on that one. And so basically what we are looking at is that you can modify the intensity distribution of a light beam by choosing appropriate polarization and the spatial degree of freedom. That was the spinning disks that I showed in the first slide. So I can have a control over that one. So basically I can control the intensity distribution and the propagation path and vice versa by controlling these degrees of freedom of light. This is something to keep in mind, that it is inherent in all optical processes and plays a crucial role in the modern way of understanding light first, and then subsequently the light matter interactions. Some of the milestone articles that we should keep in mind is that this was the article written by Poynting, which says that light does carry spin angular momentum. That was the first paper that he wrote. And this paper, which came in 1936, was the first demonstration, experimental measurement, that light does carry spin angular momentum. You can spin an object and then carry and calculate and measure how much of spin angular momentum is transferred from a light to a medium. This was a Betts paper is a very historically significant paper. And this paper, Professor Omatsu already showed in his talk. This was the first paper which came in 92, which talks about the orbital angular momentum aspect of light. So we cover both the spin and orbital angular momentum of light. And the spin-orbit interaction as a phenomenon was first proposed by Zeldovich in 92. So you see, they are not very old. They are in hundreds of years of history of light, these 90s, and they are very, very recent, this one. So this was the first paper where he talks about the spin-orbit interaction. This inhomogeneous medium that he talks about is actually an optical fiber. Is a classic example of that. And Blyock subsequently said that light does carry angular momentum, and it does all kinds of strange things, even in the simplest of the processes of reflection and refraction. And then he considered the light to be an electromagnetic wave packet. He subsequently wrote a research review article, Spin-Orbit Interaction of Light, that basically revolutionized this whole area of research, because now you start looking at the light in a completely different way compared to what we have been doing all these years. Quick introduction on the spin angular momentum. You can see here that the electric field vector is kind of circulating around the axis. So because of that, it carries a spin angular momentum S, and sigma is the helicity of the electromagnetic wave. If it is +1, it is right circularly polarized. If it is -1, it is left circularly polarized, and it is normalized with reference to the direction in which it is propagating, and it is a longitudinal angular momentum that we are looking at if you take the electromagnetic wave to be a plane wave, right? So that is an ideal case, right? And sigma is parallel to the z-axis or the propagation direction of the light that we are looking at. Now, I can kind of look at it in two ways. One is that if you look at the propeller kind of a thing, it is propelling. So that means that your electric field vector is oscillating along the direction in which, perpendicular to the direction in which it is propagating. We can also have spin angular momentum as a spokes of a wheel. That means that if this is the electric field vector, you can see that it tumbles. It is like a spoke wheel, right? So it kind of goes like this. So that means that you can have an angular momentum, spin angular momentum, along the direction in which it is propagating also. So this is the two ways that you typically look at it. One is perpendicular to the direction of propagation, one is along the direction of propagation. There is nothing stopping us from expecting that electromagnetic wave does behave like this. The Maxwell's equation still allows for all these things, right? So that is something that one has to kind of keep in mind. And the simplest way to represent in a geometric fashion is that you look at polarization as a polarization ellipse. Under certain condition, it becomes linear. Under certain conditions, it becomes elliptical. I can represent it on a Poincare sphere. Your poles are S3 plus 1 and minus 1, and your equator is basically a linear state of polarization. That means that it can go from horizontal to vertical through plus 45 and minus 45, right? And all these things, this chi and eta, are basically the quantities which I use to represent the state of polarization on the Poincare sphere, right? I am plotting it as Stokes parameters, S1, S2, S3, right? And important thing is that I can now think of a way to manipulate it. Now, I take a combination of a quarter wave plate, half wave plate, and a quarter wave plate. It is a QHQ combination. That is the first example of saying that it is a geometric phase that comes into picture, and that geometric phase is known as a Pancharatnam-Berry phase. You look at it like this. So I have a circularly polarized light that is represented by a point on the Poincare sphere as the pole, and it goes through a quarter wave plate oriented with its opposite axis in a particular direction. So if I put it at 45 degrees, then that circularly polarized light becomes linearly polarized light. It comes to the equator. I put a halfway plate with the orientation in a way that the polarization state of the light after from here kind of turns around because of the halfway plate, that it rotates the polarization by 2 theta. It comes here. And I send it through another quarter wave plate which is oriented in such a way that that state of polarization is taken back to the pole. So in the process, I have covered a solid angle of the sphere, and that solid angle is your geometric phase associated with the omega, right? So this is the way to kind of understand your emergence of geometric phase in a very, very simple QHQ kind of a wave plate combination, and that is your Pancharatnam-Berry phase. So now you can think of that you can keep these orientations in different ways. Now if I rotate this halfway plate, I can basically come from the pole to the equator and go back to the pole in different trajectories. So that way I can manipulate the amount of geometric phase accumulated by a beam of light. Now, quick introduction on the orbital angular momentum. Professor Omacho already said that it is called a Laguerre-Gauss mode or a donut mode. Now, depending on where I measure the momentum of this one, the light or the photons take different kind of trajectories. That is what is represented here. Similar to the spin angular momentum, I can also define orbital angular momentum quantum number, which is this capital L. And now, instead of electric field of an electromagnetic wave going in this direction, now I have a phase, because I was telling, right, it is not a plane wave, but it is a helical wave. Now the wavefront is helical as it travels along this direction. So that is your z-axis, and then my electromagnetic wave front, instead of a plane wave or a spherical wave, it is a helical wave that I am looking at, and it carries with it a momentum which is proportional to L. L is the quantum number, and that is a charge of the vortex that was being referred to. So I can kind of use this formula to find out how much of angular momentum does my beam of light carries, right? So it is the simplest of the structure of a vortex beam, as was shown earlier, that it can take any number of charges. It can take +1 or -1, plus or -2, or plus or -3. And this is how the orbital angular momentum phase structure is going to look like. This is the intensity profile. This, if you associate with the circularly polarized light, this becomes a linear counterpart of that. These are called Hermite-Gauss mode. And so this is a 2-lobe or a 3-lobe or a 4-lobe kind of a thing. There is a phase dislocation that comes into these kind of beams. So these are all the optical modes associated with the spatial degree of freedom of light. So similar to Poincare sphere, I can represent a modal sphere. So similar to circularly polarized light, I have a Laguerre-Gauss mode on the poles, and I have a Hermite-Gauss mode on the equator. And all the mathematics exactly maps with a linearly polarized light to circularly polarized light. I can do exactly the same mathematics across the modes also. Similar to what I do for QHQ kind of a combination, I have a combination of optical elements which I can use to manipulate the geometric phase accumulated because of the modes. So that is what is shown here. So on the modal sphere, I can now adjust how much of phase or the geometric phase that my beam of light accumulates as I kind of make this transformation of the optical components, right? And there was a very nice article in PRL in 2003 where they have measured the amount of geometric phase. As you can see here, you can see that as I rotate the amount of geometric phase accumulated, you see that the mode is rotating across the axis. So that is the way I know that I can quantify the amount of mode, not by polarization, but by the spatial degree of freedom or the intensity at which the light beam is going to be the maximum. So you see that it is rotating around that, right? So that is the association, exactly identical to what you have done for polarization, you can now do for modes of a beam also. One more aspect to this one is the direction. Now we were saying that light kind of travels straight, but I can make this travel in a three-dimensional space. So that is what is being done here. So I have a beam of light that is coming along the z-axis. So if you see here, similar to the Stokes parameters, I am now representing in the direction space kx, ky, and kz. So I take a beam of light which is traveling along the kz direction, along the z-axis. That is starting here, the blue color. Now I put a mirror here and then turn it around along the x-axis. So the polarization or the direction has come from kz to kx. Now I put another mirror and then take it from the x direction to y direction. So that is what is happening here. I am going from x to y. And then I put another mirror and then come back to the z direction. So now in this process, I have again covered a trajectory of directions. Now by tracking this trajectory of direction, now I can find out how much is the geometric phase that is accumulated by the beam of light. So now you see that the three aspects of light, one is the polarization, one is the mode, and the other one is direction. All of them independently contribute to the geometric phase, which is the fundamental nature of the light. And then we will see now how I can manipulate these 3 degrees of freedom to extract a lot of interesting physics from this one. So now I will take a simpler case of a spinning light beam. So that basically means that I can take a beam of light which is helical wavefront or a vortex beam kind of a thing, and then I give it a degree of an additional degree of freedom which says that I am making this helically structured light beam polarization also. That means that in addition to helical phase front, it also has circular polarization. That is what it is given here. If I take a circularly polarized Gaussian beam, the wavefront is going to look like this. If I take a helically wavefront beam and Laguerre-Gauss mode, the phase structure is going to look like this. Now I take this beam and then focus it, and then I trap a particle. This was shown by Professor Omatsu also. Now people have measured that the particle is spinning around its axis. That is the blue arrow that you see here. And it is not only spinning, it is also going around a trajectory. That basically tells you that now you have a beam which has both spin and orbital angular momentum, and they both are playing a significant role in manipulating the trajectory of a particle that is caught in a tweezer. Right? So that is the first demonstration to say that the spin and orbital angular momentum do play a role as far as the trapping or a tweezing of these kind of particles are concerned. Now, when I say spin-orbit interaction, I have taken these 3 degrees of freedom and then I have put them under one roof. Right? So I have a extrinsic orbital angular momentum, which basically tells you that the direction in which it is traveling, it carries a different amount of angular momentum. And I have an intrinsic orbital angular momentum, and now I have a intrinsic spin angular momentum. So now I am distinguishing between the trajectory and the intrinsic nature of the beam. These are the 3 things that I introduced. You put them together, then you come across as a spin-orbit interaction of light. Now you have a spin, extrinsic orbital, and intrinsic orbital angular momentum. When I say spin-orbit interaction, it is the convergence of these 3 degrees of freedom of light. Now we will see what are all the things that it can do. I can represent it in a geometric sphere space also. This is what is your Poincare sphere that I showed. This is your modal sphere, and this is the momentum sphere that I have. So together, these are all tensor multiplication. So your beam is going to have a complete spin-orbit interaction as a tool to see what are all the things that it can do. Right? Most important thing, every physical parameter should have a conservation law. So we have also shown that the angular momentum aspects that we are talking about, the spin and the orbital, intrinsic and extrinsic, all of them follow conservation laws. Now, so we are not going to talk anymore the angular momentum in terms of spin separately and orbital separately. We are going to talk about it as a joint process. It is a sigma plus or minus L. So it is the total angular momentum of the photon that you are going to talk about, and it is a conserved quantity following all the conservation laws that we have studied so far. If there are any questions, I will take it. Otherwise, we'll move forward. Questions? Quick. Doubts, clarifications?
Does anyone have any questions?
I finished about half an hour. That is to basically introduce you to this. For me, it was new, 10 years back or 20 years back. So yeah, this is almost my evolution of how I understand this area of research. Okay. Will we move forward? Okay, good. Now, first example of SOC, which is spin to orbit conversion. Now I have a beam in which I have both spin. Okay, let us say that I have a beam of light which has only spin angular momentum. That means that I am taking a Gaussian beam of light which does not have any orbital angular momentum. For a Gaussian beam, the orbital angular momentum is 0. But I am giving it only spin angular momentum. That means that it is circularly polarized. If I look at it as a wavefront, you see that the phase is changing across. I take this beam and then I focus it. So you can see here that I put a lens. I send a circularly polarized light of polarization sigma, and then I am focusing it using a lens that we are having. Now suddenly I see that when I do that, you see that the particle that I have trapped on the tweezer is not just spinning, but it is going around an orbit. Right? You can see that, right? It is rotating in the clockwise direction. I go from sigma +1 to -1. It is going in the other direction. Now suddenly you see that a beam of light which has only circular polarization is behaving as though it has orbital angular momentum. So then people went back and then calculated and found that this Ex, Ey and Ez that I said earlier does indeed have a orbital component that comes with that, and it is this component which is making this beam rotate around an axis as though it is possessing an orbital angular momentum. So that is almost the first example of spin to orbit conversion. The beam has only spin angular momentum, but because of the way that you have prepared the beam and you are focusing it, it has acquired an orbital angular momentum attribute. So that is your spin to orbital angular momentum conversion, and that has been demonstrated by tweezing it. Now, not only that, it has all kinds of other dynamics also associated with that one. So this is one of our work that we did. All I do is that take a beam of light, it is a Gaussian beam, and then I focus it with a lens, and then I simply reflect it, put a mirror and then reflect it, and then I measure the polarization state of the light. As I said earlier, the cross polarization of the light is going to give you this 4-lobe pattern in the orthogonal component, and then I get a beam like this, and then you will see that this beam does funny things. You see here there are two eyes here. Now all I am doing is that I am basically changing the polarization filtering process. You see that these two eyes that are there, they will merge with each other, and then they will go in the orthogonal direction to the original part. This is the CCD image caught with the camera, right? So now you see that a sad face becomes a happy face suddenly, right? If you want to look at it. Right? So, I mean, we were very happy when we saw this one. So, kind of we were trying to understand that simply by putting a mirror and then rotating my analyzer, I am seeing that the dynamics of the beam that we originally saw only as a Gaussian beam, we all know that if you take a Gaussian beam, polarize it, and you put an analyzer and rotate it, it will go from maximum to minimum. This is your Malus law, which was written in the 18th century. But this, we are doing exactly the same thing. Only thing that extra that we have done is that we have put a lens. This is not any special lens. This is your ordinary lens that you have in your lab, 5 centimeter, 10 centimeter focal length. But suddenly I see that the beam is doing some strange things. So we chose to figure out to understand that these two dark points that are there, they are not just any other dark point. There is a singularity that is coming in that. So you can see here, I take this beam and then I interfere or superpose with another Gaussian beam. That is what you do in interferometer, right? You take a beam and then superpose it with another beam. You see that at the place where the dark spot is, I see that the interference fringe becomes suddenly a fork, right? It is a single fork if it is a single charge. If it is a double fork, that means the charge of this vortex point has charge 2. I flip the polarization here, the fork kind of goes up. So now you can see that there is one fork here and there is one fork here corresponding to these 2 points. And then when the at certain location, it becomes the two merge, and then I see a charge 2 vortex, and then the vortex positions changes. Suddenly I see that spin orbit coupling is just not a simple any other process. It has some interesting dynamics associated with that also. I am going to rush through these results as slides, but if there are any questions, we will discuss it later on. Right, so this is one of the results that we published. Now, if you look at this pattern, this looks like a symmetric pattern, right? With reference to the center, these 4 lobes that we talk about are exactly symmetrical with reference to each other. Now, you would have studied in your Hall effect in your condensed matter physics that whenever you break the symmetry, whether by artificially imposing a inhomogeneous magnetic field, or whether you spin the electrons in one way or the other, or you apply some current, you break the symmetry and the Hall effect comes into picture, and that is exactly what we have done here. So we have taken a focused beam. So this is the polarizer, focus it. Instead of focusing it in free space, we are putting a halfway plate, or sometimes we have done it with a polarizer also. But instead of putting it orthogonal to the beam that is coming in, we have just little bit tilted it. And then rest of the things is that we again collimate it and then put an analyzer here and then we measure it. Depending on the orientation of the analyzer, you see that here the 2 lobes are there because I am breaking the symmetry. The 4-lobe pattern here, I am looking at only these 2 lobes instead of the 4. That is this. If I rotate the analyzer by clockwise or counterclockwise, I see that only one of the lobes are coming. That essentially means that I am now selecting the spin of the photons. That is what this S3 basically gives you. This is the Stokes parameter. I see that the beam has on the one side left circularly polarized, and on the other side it has right circularly polarized. Now I can select which direction the photons will go. If it is right circularly polarized, it will go in one way. If it is left circularly polarized, it will go in the other way. So now I am using a light, and by appropriately arranging the configurations of what I do, I can now spin select the direction in which the light is propagating, and that effect is essentially what is known as the spin Hall effect of light. Now, as I said earlier, if the spin of the photon can do, orbital angular momentum can do exactly the same thing. So now if you take the orbital angular momentum, that earlier I showed that the vortex beam are symmetric. Now, depending on the direction in which this vortex beam is traveling, if it is going in this direction, you see that the weightage of the mode is going to be on the one side. If it is traveling in the opposite direction, it is going to be weighted on the other side, right? So the mode becomes asymmetric. So that is what is the orbital Hall effect, right? Similar to spin, if the photon is spinning in this direction, it will take this direction. If it is spinning in the other way, it will go in the other direction, right? So that is what we have done in this case. We have, if you see this graph, we have selected modes of different orbital angular momentum quantum number 1 to 5. And then I am giving this whether it is clockwise rotating or counterclockwise rotating. Depending on which direction it is rotating, you can clearly see that whether it is the top side of the mode or the bottom side of the mode becomes heavier. That tells you that now I can exactly find out which way the mode is propagating by adjusting this the rotation direction of my orbital angular momentum. I wanted to tell Omatsu-san that this was published in his journal in 2019. I kind of OSA continuum it is. I published a couple of articles when they made free. After they made money, I stopped doing it, but anyway. Anyway, so, okay, some more exciting things. Now, I can do in whichever way now. Now that we are slowly understanding what the light is doing, so I can take a right circularly polarized Gaussian mode, and I can take a left circularly polarized Laguerre-Gauss mode. I can somehow find a way of superposing these two. I get a pattern whose polarization is absolutely strange. Now, if you see here, the center is circularly polarized, but as I move away from the center, it becomes elliptically polarized light, and at some point it becomes linearly polarized light. Now, one beam of light for me has all states of polarization. It is circular, elliptical, linear, whichever way that you want. Now, this is in a particular pattern, and that is called a lemon pattern, because these are all topological structures. That is why we also call this as topological optics. Now, you see that if you go around that, the polarization ellipse rotates in a strange way, half circle. Now, if I flip the orbital angular momentum and spin angular momentum aspects of it, I get a beam which looks like a star. You can see that at some places it is linear along the 3 arcs, and everywhere else it is elliptical. So these star and lemon patterns of polarization of light in a single beam of light. So one beam of light has all states of polarization that you can think of. This kind of patterns we have generated using an optical fiber. Right? So that was published in this journal. Not only that, we have come across, similar to the Poincare sphere, we have come across, we proposed a C-point sphere. We will not go into the details. So that means that whether it is lemon or star, or in between that there is a new topological structure which is also known as a monstar, not monster, monstar. So it is a combination of lemon and star. So somebody coined these words in the topological mathematics part of it. So we have all fundamental topological structures that is ever present, whether it is any area of research that you talk about. As far as science is concerned, these kind of patterns have been observed, and now we were happy to kind of see that you can generate in an optical beam of light, and then we can manipulate it the way we want. Huh? The output. So this is the setup. So you take a beam fiber, you lay it horizontal, and then you send a polarized beam of light and you focus it into the fiber, and then at the output you will get it. I don't have anything else. Simplest, yeah, it is, only thing is that it is not a single mode fiber, it is a 2-mode fiber. You have to excite one more additional mode. That is what this Laguerre-Gauss mode is about. Okay, now fiber is over. Now we will send it through a crystal. This is the crystal that all of us use, uniaxial crystal, nothing special about it. It was just lying in the lab, and the setup is the same. You polarizer, put a lens, and this arrangement is called a conoscopic arrangement. I put a crystal in the focal region, and I look at the output, and output looks like this. All of us who have done experiments would have seen this. This is the 4-lobe pattern that I was showing earlier also, that there are, if you want to look at it, there are 2 kinds of interference patterns that are there. One is that if you go around in the azimuthal direction, you have a dark, bright, dark, bright, dark, bright, right? So around the azimuthal direction. Now if you go radially away, so you have a dark, bright, dark, bright, dark, bright. So it is in the radial. So this has a, whenever the intensity is bright and dark, it's an interference pattern. So you have an interference pattern in the azimuthal and radial direction. Now we kind of did some mathematics and then kind of found that this has 2 kinds of patterns that come because of, one is a dynamic phase part of it, and the other one is a geometric phase part of it, and then we did some mathematics to show that you can actually separate these 2 effects in this crystal and then kind of understand it. If you put them together, you see a polarization pattern which is as complicated as this, right? You see that it is, the polarization is spinning in all kinds of direction. Here it is counterclockwise, in this direction it is clockwise, here it is counterclockwise. So all kinds of things are happening that corresponds. So these patterns that you see are not just intensity pattern. There is a lot of polarization information that is lying underneath that one, right? So that is what we showed just by propagating through a uniaxial crystal. Not only that, we did some GRIN is your graded index medium, and so the pattern that you get in the output is, this is a Muller matrix analysis, but don't worry about that. Some way that we kind of extract the phase and the polarization information about the light that is propagating through this rod. Not only that, we did some interesting mathematics also. So if you see on the top, you see that I can send any angular momentum state of the beam, and on the y-axis I can change the spin angular momentum aspect of it. We just measure the output. If the charge is 0, that means I am sending a Gaussian beam. You see that it is a charge 2 vortex that is there. But moment I go to charge 1, this becomes 3 and this becomes 1. Here it becomes 4, this becomes 0. So this is your Gaussian beam. So you see that a lot of interesting things happen. This is the other paper that we published in OSA Continuum, that when it was free. Now, the simplest of all is this, generalized reflection. You take a beam of light, we put some polarization components, don't worry about that. This is standard. I put a Glan-Thomson polarizer and put a quarter wave plate to make it spin, circularly polarized light. I simply take a glass plate and then reflect it. At Brewster angle, which is what we all studied, they say that the intensity goes to 0 at Brewster angle, right? Actually, it is not correct. You see that this is the intensity that I get at Brewster angle. There is a dark point, but around that, there is a modal structure that comes in, and we went and confirmed that there is a vortex structure around that. So Brewster angle is not just an angle, but it has a vortex structure underlying that. So that is the kind of polarization map that we did to show that it indeed has, so at different angles you can see that we have done these measurements and then simulated it also. Now I'll show that, so this generalized reflection that I talk about is done in a movie form, so you will see the changes that it is going to go through. Now what you see, the 2 things. One is that theta I is the angle of incidence, and theta E here is the ellipticity of the light that I'm sending in, right? I'm going to see that these 2 changes, and you simply watch the polarization changes that is going to happen in this beam. You see here, I'm changing the ellipticity. You see the pattern is changing here, and you see that simultaneously the intensity pattern is going to change here also. Right? You see that initially the mode was on this side, brighter, and then at one point of time that both the sides were of same intensity, and then the left side of the mode became stronger. Now simultaneously you should see that the polarization in the cross section of the beam also changes dramatically. This is just a reflection that we all study about, right? I'll just run it once again so that you can see. This green circle here corresponds to the polarization state that we are looking at. Let us say that this is right circularly polarized. Polarization remains the same, but now I will show you in the next one in which the polarization also changes. Now, and ellipticity same. This is again a reflection. You will see that their angle of incidence, the beam also almost uniform in the beam cross. Is coming into the cross section, and so you see that right circular becomes left circular, and that is the Brewster angle in which the polarization is extremely complicated in the beam cross section also. And then it becomes uniformly polarized, almost. But these lines that we are talking about is just a guide to the eye to see that how these topological patterns that we talk about, the star, lemon, and node, and all kinds of other patterns change even in the simplest of the reflection. Second part of the talk is over. Questions? Burning questions, yes. Yes. Now, okay, why do I care? First thing is that as a researcher, I should not say that why do I care, because these are not in any books. It's an interesting research problem. Nobody ever did this one, right from Fresnel to Brewster to whomever you want to name. Nowhere in the book you will see that a simple reflection process is going to give you a beam which has all states of polarization. If you tell this to anybody, they will laugh at you. What nonsense are you talking about? Now we have shown simulation and experiments, and most importantly, we have published it. That means it is peer reviewed, right? All of us are PhD students. So no questions. It is a scientific fact that it has been established. That in itself is interesting because we are kind of telling something very, very different from what has been taught to us when we were children, right? Or when we were young. Now, I actually was stopping at that point of time. I said I don't care anything more because the physics that I have found out is new in itself. That is, I am happy, I will go to sleep. But then people kept on asking, why do I care, right? What is the use of these kind of beams? Okay, then I thought, okay, we will do this also. So we measured some chirality. So don't worry about this part of it. We have done it in a different way. All I would say is that at this place, the beam that I have generated has a structure that I already showed, right? I will show those, I will show that image also, right? So this is the beam that I am getting. That means that at this place, it is more or less linearly polarized. But as I go away from the radially out, it has some ellipticity. It is the same beam that I showed earlier, right? So if I measure the Stokes parameter, I can say that the top part of the beam has right elliptically polarized, bottom part of it is right elliptically polarized, and I can represent it on the Poincare sphere as though it is kind of a little bit of patch of light on the Poincare sphere x-axis, right? So that is the beam that I have generated here. I wanted to measure the chirality of a quartz rotator, standard quartz material, nothing fancy about it. I put the quartz here, and then I put an analyzer, and then I measured the intensity of the light that is coming out. Now, you can clearly see here that what I am measuring here is the shift in the beam. You remember that the two lobes go up and down? That is the shift that I am measuring. That is what I am plotting on the y-axis. And on the x-axis, I am selecting which polarization that I want to measure. So I mean that I am rotating my analyzer with reference to 0, or it means that it is cross-polarized. I can clearly see that it has a very, very strange behavior. This linear part tells me that how much of chirality is there in the quartz rotator. So now if you give me any material which is chiral, I can use this beam and then directly measure it. And the important thing is that it is there in these two papers. I am not going to tell that. We have shown that the commercial polarimetry that is available in the market, you tell this to chemist people, they will say that it is 1 millidegree. We have shown that the sensitivity of this method that we have done is 10 times better than that. It is the simplest of the methods we can talk about. Not only that, this you see the pattern here, it is the lemon pattern that I talk about. You see that the trajectory is like this. And we generated the beam with the same setup and then send it through the quartz rotator. Now you can see that instead of this kind of a beam shift, the mode rotates. So if you see here that the original position is in the straight line here, then it kind of becomes a dotted line. You see that the rotation is, we can measure the amount of chirality that material has by simply monitoring how much dark spot is going to rotate, and the sensitivity of this method is shown to be much better than the existing commercially available method. So that we can use these kind of beams with the complex polarization structure to measure accurately and sensitively chirality of material in single shot. Chirality measurement, you have through a lot of circus. So, but these are much, much simpler compared to that. Not only that, we can measure or use these kind of beams in a magnetometer also. So we have done the same thing. So generate these kind of beams and send it through a atomic vapor, rubidium vapor, and then you can apply some magnetic field, and the magnetic field interacts with the beam, and then you can again do the same kind of beam shift measurement, and then we can kind of find out that we have been able to demonstrate that the sensitivity is about 1 nanotesla of the magnetic field that you apply. I can see that the sensitivity, the mode basically shifts. So these kind of inhomogeneously polarized beam is useful for these kind of using it as a magnetometer. And more recently, we have used it as a MOC also. I don't know, people who know MOC is magneto-optic Kerr effect. That means that you apply magnetic field and you measure the Kerr effect in this one. So we have used the spin Hall effect to measure the Kerr effect in material. And you can clearly see that if the material is magnetic, I can measure the hysteresis loop of this one using the beam that we have been talking about. And the sensitivity is much better than the commercial MOC you have here. Yes. Now you know what is the reference for this work. This I did with the TIFR people. They sent their sample here. They measured with a commercial MOC. They measured it in the lab, in my lab with this one. Our method was much, much more sensitive than the commercial MOC. And that was published in the JAP. See, I'm an optics person who keeps on changing new things. So that setup can be made anytime. That is not a big deal. But yes, we have shown that the Kerr effect also can be measured. Anything which involves mode rotation or polarization change, anything that you talk about, we can measure it using this spin Hall effect. I will just give 3 applications. I hope you will be convinced about it. Many, many more things can be done. We are pursuing some, but we are not interested in many. So I'll just summarize it and say that understanding the spin-orbit interaction of light is of fundamental importance, no matter what. And I would say that this is the way to understand light. Whatever we have done in the past, you simply say that that is not sufficient to explain many things that is happening. And because you understand that, we have been able to demonstrate novel measurement schemes, which shows that they have higher sensitivity, accuracy beyond any of the conventional techniques. We are just using light, understand light, all the other aspects that come in the light and use it for some applications. And these are all kind of comes back to the fact that it is all follows Maxwell's equation. There is nothing new about it. We are only kind of breaking down some of the incorrect things that were taught to us and then kind of looking at it in a little more inclusive way. And as I said, this is inherent in all optical processes that you can think of, not only of light and when light interacts with matter. And the modern way of understanding optics, this is the direction it is going all across the world. And Professor Umatsu's talk kind of emphasizes that the structured light is the way to kind of understand light and light matter interactions. And we just say that optical fields are by nature inhomogeneous, and this is there everywhere, and we only kind of starting to figure it out at this point of time. We're just starting, and then we will see where it goes. Right? These are some of the acknowledgement. Of course, students and postdocs are the backbone of all these work, and of course, their fellowships, projects. And these are some other people whom I have interacted with from some time, from Berry to Bliok. Some of them are my collaborators, some of them are inspirators. What do you call that? Influencers. Your YouTube or whatever, Instagram. Like that, they are for me. Whatever, yeah. Wherever I get a chance, I talk to them. This person is no more. Saskin is passed away. He is known as the father of singular optics. Anyway, thank you. I'll take more questions.
Thank you, sir, for your presentation and your, lecture on singular optics. We would like to give you a token of our gratitude.
Students would be convinced, it's all right, I'm loud enough. The student would be convinced why I was persistently following him for a talk here, right? So he's completely has given a very new flavor. To the best of my knowledge, we are not doing any research in that area. Research is all about what you are doing, what others are doing, how do you collaborate with them, enrich the physics and understanding of it. So this is pretty much the reason why I was following you up, I was requesting you, you must come. So there was a discussion came in, for the speakers. And I said, like, Thomas is coming. So he mentioned about someone, the father of singular optics. So I would say the father of Indian singular optics is Professor Nimal.
Actually, three of us started it. Myself, of course, I was one of the first people. Senthil Kumaran from IIT Delhi and RP Singh from Kerala. We started this area almost about the same time. 2003, 20 years.
Thank you very much. Really, So I think, some of you may hesitate to ask questions, but please, feel free to interact.
Yes, I'm a teacher for first thing. I teach kids like you every day. Right? Teaching is our profession, so yeah,